Okay. All right. I'm Philip Lubin, University of California at Santa Barbara. I want to talk to you today about approaches to relativistic flight. If you're interested in the details, please look at the paper called The Roadmap to Interstellar Flight. It's on the archives. It's also on our website. There's actually two programs going on here in parallel and in synergy. We're in phase 2 of a NASA program funded by the Advanced Projects Office at NASA headquarters. We just started phase 2 last year, and we're also funded by a private donor, as well as the breakthrough initiatives. So this is, and it also involves MIT Lincoln Lab, which is a federally funded research lab. Okay, let's see, forward here. So sometimes people ask, why go anywhere? And since you're all here, you at least decided that you didn't want to sit home and watch us on the big screen. Although I did notice that some people were watching the big screen in the other room, so that's an example of remote sensing on different ways. So I think this is a good place to start, since some people say, why should we go to a star? What sense does that make, right? We have lots of problems at home building large telescopes. Why don't we solve those problems first, right? If those of you remember the space era in the 60s, you might see an analogy there. If you don't, then you won't. Okay, so why should we visit anything? So I claim in a general statement, all exploration is remote sensing. Looking at you is remote sensing, right? I'm not inside your molecules. I don't know what you're doing, all right? Everything is remote sensing. Even when you touch a rock, it's remote sensing. So astronauts are remote sensors. It's just a question of how remote. Okay, we're obviously not proposing that people stop building telescopes. And in fact, the array that we're going to be building is in fact a phased array telescope, because it can both operate in a transmit mode as well as a receive mode. So the spot size, for example, at 4 light years from 1 kilometer phased array telescope is about the size of a stellar disk. And that's interesting. So for those of you who are interested in doing, being able to block the light, well, this blocks light by the fact that the size of the beam is so small. It's actually much smaller than a typical solar system. Okay, so let's do a quick calculation in our head. Suppose I had just a measly 10 centimeter optic at 1 AU, which takes about 40 minutes, by the way, to cross at 20% speed of light. It's not seconds. It's actually close to an hour. You would need, for the equivalent resolution at the Earth, which is 250,000 AU away from the nearest star, 250,000 times 1/10 of a meter, which is a 25 kilometer telescope. So we could build a 25 kilometer space-based telescope, and that would be interesting. I'm all for that. Okay, but that's the equivalent resolution to a 10 centimeter optic, 1 AU, from a target. Well, why do we have to be 1 AU? What if we're 1/10 of an AU? Well, then you got to build a 250 kilometer telescope. And what if I'm 100th of an AU away? Then you're going to have to build a 2.5 megameter telescope. So we can keep playing this game, but clearly there's a synergy here. The other thing is, in this system that we'll talk about, you could actually launch a new mission every few minutes. This completely changes the paradigm in space exploration. In Starshot, as opposed to NASA, we're talking about launching one maybe every few days. The system could run 24/7. You could launch every few minutes in theory. Okay, here's a good one just for your classes if you teach. If you took all the mass in the universe and converted it into chemistry, you could not get a single proton up to relativistic speeds. Okay, so try that on your class as a homework problem. Take all the mass of the universe, convert it into chemistry, and you will find that the speed ratio will not even get one single proton, which is your payload, to a decent fraction of the speed of light. Okay, so you got to have a different paradigm. Chemistry is not going to work. That chemistry hasn't changed in 1,000 years in terms of rockets. The rockets 1,000 years ago had almost the same ISP as we have today. So chemistry will indeed get us to Mars, but it's not going to get us to the stars. Ion engines don't work, solar sails don't work, nuclear thermal engines don't work, fission engines don't work. Fusion engines, which some people tout as being the answer, really don't work when you look at them in detail, because fusion is less than 1% efficient. Look at a thermonuclear weapon or read our paper, and you'll see what the conversion rates are like. It just doesn't work, except for extraordinarily large scale systems. To get to relativistic speeds, you need relativistic exhaust. And that leaves 2 possible problems, barring new physics: antimatter annihilation engines and directed energy. So directed energy is the one we've chosen, and that only works when you leave the directed energy system at home. So here's things that we've accelerated up to high speeds. This is speed, this is beta, this is gamma minus 1. At the lower end, the particle end, we get to within a meter per second the speed of light. At the upper end, we're quite pathetically slow. Voyager, which is going less than 20 kilometers per second, would take up order 100,000 years to get to the stars. That's not a viable path forward. I'm a little bit too impatient for that one. So it's most likely at this point that the nearest first missions to the stars will ride a beam of light. Because, in fact, the exhaust is relativistic. You reflect it off a reflector, and that comes off at the speed of light. So, in fact, you have a relativistic exhaust system. It's only on for a few minutes for the lightest missions, which means you could, in theory, not what we're playing on Starshot, in theory, you could launch hundreds of these per day. Okay, however, this is not only limited to one tiny system. Here's a plot from a gram to 10 kilograms, and this keeps going out as far as you want. If you want to get to relativistic speeds, here's 10% the speed of light, here's the speed of light. You can get above 10% the speed of light with things which are in the order of hundreds of grams, and if you're willing to go to a few percent the speed of light, you can go all the way out to 10 kilograms, which is interesting. So you should keep that in mind. It's not just about the tiniest things. And while this is less tuned to Starshot, the same technology gives you that capability. Once you master that technology, a whole set of things opens up. So how are we going to do it? How will we make a bright enough laser pointer, which I can barely see the screen? You probably can't see it at all, so this is not that bright enough pointer. The idea is to use what's called a MOPA system, which has one single puny laser, which can be rather small, and then you split it and you amplify it, and then you beam combine in space. So there's no beam combining in a telescope, you're not beam combining in fibers, things like that. Okay, so there's no limit to this technology in terms of upper limits on power. It's a modular system. It's very analogous to parallel processing supercomputer. So the way you make supercomputers, take lots of little processors and gang them together. Well, we've already started making these in the laboratory, so prototyping has begun. We have some laboratory tests, which I won't bore you with, but actually looks pretty good. This is a 19-element phased array, which I carry in a little suitcase to show people. Makes the TSA very happy, by the way. So they've never let me take it on board, because they think these things come out the back don't look very nice. It reminds them of something else they don't like. And then we've begun long baseline interferometry tests. So we have a 25-kilometer baseline interferometer in our laboratory. And actually, the power spectrum, which is not, this is not the appropriate audience to show you, but it looks actually quite encouraging. And if you want the details, come and see me. Also makes nice pictures. Okay, however, suppose you wanted to get somewhere rapidly in our solar system. Let's say you wanted to go to Mars really quickly. Well, we could have an in by 9, out by 5, and those of you who are old enough might remember what that stands for, which was cleaning. You could have same-day delivery to Mars with small packages. So here's time, and this is days on this axis, as a function of payload mass, and this is for the kind of large system we're talking about building here. It takes about 8 hours to get to Mars with a kilogram. It takes about a day with 10 kilograms. If you want to send 100 kilograms, it takes of order a couple days. That's really interesting for people that might want to rapidly shuttle things back and forth. In fact, humans, which are up here, here's 10 tons, here's 100 tons, are actually reasonable time scales. So this technology is useful for many things. The moon takes an hour to get to the moon, including stopping, by the way. This includes the stopping portion, which is important, although we do charge extra to stop. Okay. So we sell the one-way tickets with not stopping. They're very cheap. So maybe we can get Amazon to buy into it. Okay, so we built little tiny spacecraft, and I actually have some in my pack if you want to take a look at them. They're currently down the size of a quarter, and they include laser comm on board and FPGAs and processors and magnetometers and accelerometers and cameras. But I would claim that we probably don't want to do that, and I'll show you why. Small is nice, but in fact, size matters here. Okay, maybe you want to build a wafer-scale spacecraft that's really large, but really low mass. Well, how do you do that? Here's an example of some recent technology being done at IBM, where you use silicon, but extremely thin silicon. The silicon in all your laptops that everyone's playing with right now, because they're not interested in what I'm saying. It's okay. I'm not offended. My students do it all the time. The silicon in there is a few hundred microns thick, just for handling purposes. But the actual layer that's important for the semiconductors is only of order 10 or a few tens of nanometers thick. So here's a technology which was actually very crude. They took a piece of Kapton tape, took a wafer of silicon, they cleaved it, and they peeled off the upper layer, which was electronics, like making graphene with Scotch tape. They did it with Kapton tape. And remarkably, it worked. I mean, it's crude, but that gives you the idea of where we're going. So this is a path to ultra-low areal mass density electronics. So what could you do with that? Well, imagine the following. Imagine I had not a little tiny chipsat that we've talked about. Imagine I had a 1 meter diameter wafer made on silicon, which is 0.3 microns thick. So you might want to talk to Harry Atwater. We've discussed this. This looks feasible. This is not crazy even today. Something that was 300 nanometers thick weighs about 1 gram, for example. Well, what's on that? Currently, with 14 nanometer processing on silicon, and by the way, we're pushing to 5 nanometer processing by 2020, and we're going to 3D stacking of layers, today's density is about 25 million devices per square millimeter. So in a square meter, you could get 25 trillion devices today, not 30 years from now, today. That means you could get 15,000 i7 processors of the current variety on one single wafer, which is a gram. Today, we're making wafers which are half meter, by the way, in industry. Not at meter scale yet. I imagine they will be in probably 10 years. Today, you can get 500 watts of PV. This is watts electrical at 1 AU from current multi-junction gallium arsenide cells. So what about in the future? Well, the future I'm just extrapolating a little bit from today, really not very aggressive. I'm assuming our 5 nanometers in 2020, so I'm only looking ahead a couple of years. You can get 3 peta devices per square meter. You probably don't use peta, and it's legal. Okay, this type's legal. In the future, you could get 2 million i7 devices per wafer that weighs a gram. I don't know how you power them. So this is larger than the largest supercomputer today on a single 1 gram wafer. And we could probably up the efficiency, maybe a factor 2 to about 1,000 watts. So during the encounter phase, when you have some sunlight, you'd get enough power to power at least a decent number of devices. During the cruise phase, in our baseline, we have a small radioactive generator called an RTG. Maybe you can use the wafer directly for imaging, so you don't need any sail for imaging. A 1 meter optic, or at least some decent portion of it, provides fabulous resolution, as we just talked about. Maybe you don't even need a sail, because maybe you can use the wafer as the entire system. Maybe you can put integrated photonics and electronics on one side, do a photonic crystal on the other, maybe have an entire system on a wafer. Perhaps that's a path forward. I don't know yet. It's something to ponder. It's a little bit on the aggressive side, but something to think about. What kind of sensors can we place on wafers? Well, this is today. We can do imaging devices. We can do IR imaging out to 30 microns. We can do spectroscopy. We've done wafer scale spectroscopy at UCSB in the photonics department, from the visible to the infrared. We can get Rs of between 500 and many thousands just on wafer. You could imagine an RF spectrometer. Maybe our friends use cell phones, okay? So there might be roaming charges, but I'm not sure. Maybe we could call home in a different way. You can put atomic clocks on wafers. You can put atomic scale gyros, by the way. That's an up-and-coming technology which you may have not have heard about. Accelerometers, dust impact sensors, radiation sensors, magnetic field sensors, star cameras, obviously, LiDAR modes, and the integrated laser comm on board. You can do a lot of things. There's a whole up-and-coming field called photonic integrated circuits, or PICs, which will revolutionize a lot of the electronic interconnects and data centers. So here's an example of something we produced recently at UCSB. This is a 3.5 material on silicon phased array chip, which is being used as an inverse mode for the reception. And this is what it looks like. It looks prettier in a picture, but this is the actual device. Okay, maybe we could MERV. Maybe we could take a mothership and then disperse daughters. I was going to put sons there, but I thought maybe daughters would be better. I don't know. So maybe you have a small mothership that sends out little daughters, drops them in the atmosphere. which when they hit the atmosphere at relativistic speeds, by the way, they have about a kiloton. I mean, they're roughly a gram, which is nice. We could make a little declaration of war on our friends. And then perhaps you could telemetry data back from the daughters to the mother saying, I'm sacrificing myself for the good of science and humanity back home. You could possibly do spectroscopy from the impact on the atmosphere and the surface, and there are ways to measure gravity. Oh, looks like I'm out of time. Challenges. So it's really challenging to build a phased array over a kilometer. No one's done that before. If ground-based, you have, which is the plan for Starshot, you got atmospheric perturbations to deal with. Economics are a huge problem in this program. You've got to drive the costs down to the point where you can afford it. Radiation damage, communications, getting data would be useful. And this is a hard problem. It's also not for the faint of heart. So if you want a thesis project, go elsewhere. Okay, just to give you an idea, this is communications as a function of distance. This is data rate. I put it in some weird units of the area of the transmitter by the area of the receiver, meters squared, square kilometers, don't worry about it. This is something that a couple of us are working on in the Starshot group, looking at communications. It looks possible, really hard. Use the same system you shove your system out with as a receiver. This is a good one to focus on for science. This is backgrounds, looking at the CMB, the cosmic infrared background, and the zodiacal light, thus from our solar system, from 10 gigahertz to a petahertz. So if we're going to use laser comm, which is currently my favorite, we're up here at about a micron or so. We're completely dominated by the zodiacal light. So imagine a science mission where you're going out of the solar system and you say, wow, if we're dominated by zodiacal light, suppose I get out of the solar system, then what am I dominated by? Not zodiacal light. Then I'm dominated by the cosmic infrared background, which is about 100 to 10,000 times lower than ZODI, depending on where you are in the span of 1 to 30 microns. This would be amazing for infrared astronomy surveys. I'm not proposing a JWST on a wafer. Okay, I know you think I might, but no, I'm not. But there are some interesting things you can do with modest apertures. And the mapping speeds, of course, which go like the square if you're photon limited, become 10,000 to 100 million times faster. Really interesting possibility. Okay, I won't bore you with this. This is just more things that we do. Okay, summary. So it looks like, in theory, we could get to interstellar capability by going to relativistic flight enabled by directed energy. This is truly transformational. You could have many mission modalities as well as missions and regimes. It could also be used for things like planetary defense, lots of other things. This program would truly be a watershed moment in humanity. I mean, leaving our solar system for another solar system would definitely go down in the books as being interesting. So borrowing new physics, I only see two ways to do this. Antimatter annihilation, which I don't know how to do, and also there are problems with secondary mass and the way we're doing it. And we are not limited to low mass spacecraft. Something to keep in mind. Everyone focuses on the wafers, but that's only one of the things you can push out. You build one mass driver, one photon mass driver, and you can do all these things with it. This is not a short-term program, so most of you, I'm not going to be alive when it goes, barring new medical techniques. We need new methods, both technical and economic, and what drives this program to success is actually exponential technologies, both in photonics and electronics. And I will stop there.
One over here. Can we get the mic?
Great talk. I'm new to this business, so I don't know much about it. You said communications was really hard. That's when I do the problem in my head, I come up with the same answer.
Good.
What's the power source? Do you use starlight from the star?
No, so during the cruise phase, the only power, well, the two possibilities I think they're realistic for power during the cruise phase. The baseline is a small RTG. So it turns out plutonium-238 is 400 milliwatts per gram of thermal. So if in typical converters, about 7% efficient unless you go to a new type of converter, which could be higher efficiency. So we can probably get 10 milliwatts during the flight with a 300 milligram RTG. Turns out that the collisions with the interstellar protons provide a source of heat, and that is actually a bit less, but we could probably get some power out of that. We're still kind of looking at that. Some of that's discussed in the roadmap, and there's some other papers that discuss that. I don't know yet. Both of those are possibilities. RTGs are definitely possibilities. No one's ever built an RTG that small. Some of the original pacemakers had radioisotope generators in them, which people kind of freaked out about eventually, but they weren't so freaked out years ago. Anyway, well, we've talked to people that build them. It's possible, just never been done before. Once you get to the planet and there's a star there, then you've got photovoltaics, which is vastly more power.
Last question at the end over there.
Yeah, that's a great question. So so the question was, what about the radiation dose received during the travel? How does that affect the system? I'll reinterpret your words. So that's really interesting. I actually have a plot which I could show you if you're interested later. Turns out the forward edge, you fly these things with the forward edge, forward, sorry, but you fly like this rather than like this. So it turns out the forward edge gets gigarads per year. Okay. However, when you relativistically transform the nearly isotropic radiation field, and you're going at 0.2 C, it turns out that the angular distribution of that is extremely narrow. And so the wafer itself gets very little radiation. It's basically cosmic, galactic cosmic ray radiation, whereas the forward edge just gets killed. So there's a whole discussion in another paper about how far you penetrate, what DEDX is, okay, and what the actual gigarads per year is, which I could show you if you're interested in. Okay, that is an issue on the forward edge, but doesn't appear to be an issue for the rest of it.